Suppose we have a sequence that converges to L. We want to prove that this limit is also equal to L. If you think of this here as a sequence, say C sub n, the terms of the sequence are called the Cesaro means or Cesaro averages. Before we prove this, let's talk about how to prove it, or in other words, how to come up with the proof. So in order to prove this, we want the difference between C sub n and L to be smaller than epsilon. So we want this here, and I'll go through this really quick. We want this minus L to be smaller than epsilon. Another way to write this is to maybe write it as a single fraction. So we want this to be smaller than epsilon. I'll go ahead and stop writing the smaller than epsilon part. So we have n copies of L, and we have n terms. So what we can do is we can group them together as follows. We can write this as a sub 1 minus L plus a sub 2 minus L plus plus a sub n minus L. Gotta be really careful here. Lots of nasty notation all over n. Now at some point in our proof, we're going to use the fact that our sequence converges to L. That's going to give rise to a natural number. I'll call it n sub 1. So what we can do is we can truncate this sum at n sub 1 as follows. This is a sub 1 minus L plus plus a sub capital N sub 1 minus L. And then we can continue it at plus the next term. The next term would be a sub n sub 1 plus 1 minus L plus plus a sub n minus L. Okay, and this is all being divided by n. So what we can do is we can write this over n, and then we can write this over n. Okay, and then we can use the triangle inequality a million times, and we can say that this is less than or equal to a sub 1 minus L plus plus a sub n sub 1 minus L, all divided by little n. And we could do the same thing over here, plus a sub n sub 1 plus 1 minus L plus and then plus absolute value a sub n minus L. Looks like a huge mess, but here's the idea. This first term here, if you look at the numerator, you can pretty much treat it as a constant, right? The numerator does not depend on n. So we can certainly choose little n to be bigger than some n so that this is smaller than epsilon over 2. So we got this piece, it's taken care of. And then what we'll do is we'll use the fact that our sequence converges to L to control all of these terms here, and it should work out. Let's go ahead and start the proof. And when we start the proof, a lot of what we write is going to be very similar to what I just wrote. So proof. We'll start with our hypothesis. So suppose we have a sequence that converges to L. Okay, and let epsilon be greater than 0. Since our sequence converges, that means there exists some positive integer, which again I'll call it n sub 1, such that for all little n bigger than n sub 1, the difference between a sub n and L is less than epsilon over 2. And say, why epsilon over 2? Well, if I would have kept playing with this, you would have seen that we could have taken it all the way down to epsilon, but I figured it was a bit much. Okay, so this condition here, should guarantee that this is controlled, right? That should be less than epsilon over 2 after some work. So now we have to control this. Okay, so then we can pick another positive integer. So in other words, there exists a positive integer n2, which is bigger than n sub 1. We can certainly find one via the Archimedean property, such that this term here is controlled. So in other words, it's bounded. So a sub 1 minus L plus plus a sub n sub 1 minus L over little n is less than, and we want this to be less than epsilon over 2 for all little n bigger than capital N2. And then so then we should be set. So then for all little n bigger than capital N sub 2, what we'll do is we'll look at the terms of our sequence minus L. So we have a sub 1 plus dot 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 plus a sub n, all divided by little n. And we're going to do a lot of what we just did in the scratch work. So this is equal to, again, we can combine the fractions and write this as a sub 1 plus dot 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 plus a sub n minus, and then we can multiply this by n over n, so it's really nl. And it's all being divided by little n. And now we can group each of these little a's with an L. So we can write this as a sub 1 minus L, and I'll put it in parentheses for emphasis, plus dot 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 plus a sub n minus L. It's all being divided by little n. And now we want to involve n sub 1, big N sub 1. So I'm going to write this as follows. This is a sub 1 minus L plus dot 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 plus, and then we have a sub n sub 1 minus L, and then plus, and then here we have a sub n sub 1 plus 1 minus L, lots of notation, plus dot 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 plus, and then we have a sub n minus L. And all of this is being divided by little n. Now we can use the triangle inequality several times and write this as, so all of this is less than or equal to the absolute value of a sub 1 minus L plus dot dot dot, and then plus, then we have this piece. So the absolute value of a sub n sub 1, it's hard to say, minus L over n plus, we used it a whole bunch of times here, the absolute value of a sub n sub 1 plus 1 minus L plus dot dot dot, and then plus the absolute value of a sub n minus L, all divided by little n. And we know something about this term here. We know that because little n is bigger than capital N2, right, we said it here, it's less than epsilon over 2. So the first term is less than epsilon over 2. So this is less than epsilon over 2. What about this term here? Well, this is plus, and here, each of these guys is less than epsilon over 2. So how many terms do we have? Let's think about this. If you have b sub 1 to, say, b sub n, it's clear to anyone that we have n terms. A really nice way to figure out how many terms you have is to subtract. So you take the n and you subtract this one and you add 1. Watch this. N minus 1, and then what you do is you add 1. So we have n terms. Always works every single time. Say you have b sub 3 to b sub n. Well, how many terms do you have? Well, you do n minus 3, and then you add 1. So you have n minus 2 terms. Always works. So here, to figure out how many terms we have, we take the little n and we subtract n sub 1 plus 1. So we have n minus n sub 1 plus 1 terms. So we have n minus n sub 1 minus 1 plus 1 terms. Boom, these cancel. We have n minus n sub 1 terms. So this is going to be less than little n minus n sub 1 epsilon over 2's, all over n. Okay, here is the tricky part. So this is still here. We know that little n is bigger than, we said it was bigger than n sub 2. Yep, we said it was bigger than n sub 2, and n sub 2 is bigger than n sub 1. So little n is bigger than n sub 1. That's why we could do all this. But in particular, if little n is bigger than n sub 1, then little n minus n sub 1 is bigger than 0. It's a number bigger than 0, okay? So it's this here is smaller than n. So this fraction is smaller than 1. So we have a number smaller than 1 times epsilon over 2, so that's less than epsilon over 2. Right? So we have a number smaller than 1, and it's positive. That's why we had to do this. It's a positive number smaller than 1, and it's being multiplied by epsilon over 2, so it's certainly smaller than epsilon over 2. And finally, let's not get stuck here. Epsilon over 2 plus epsilon over 2 is epsilon. And we have done it. We have proved the convergence of the Cesaro sums, or the Cesaro means. It's kind of a hard problem. I don't think this problem is easy. It took me a while to figure this out, maybe 20, 30 minutes. I hope that made sense.